The theory of the ancient immeasurable explosion is, for the most part, acknowledged by the majority of experts as the fundamental explanation for the origins of the universe, including the formation of stars, planets, and all forms of life, including ourselves. Despite its rather quirky name, the term Big Bang aptly conveys the enormity of the event. Initially, the universe was a dense mix of particles compressed into a space smaller than a pinhead. From this moment, a tremendous release of matter occurred, known as the Great Detonation. This briefly summarizes the process that unfolded over billions of years. However, regardless of the ongoing acceptance of this hypothesis concerning the universe's genesis, advancements in scientific knowledge have consistently challenged its predictions. When NASA launched the James Webb Space Telescope, the largest and most sophisticated space observatory to date, researchers speculated that its observations would support the theory of the ancient cosmic explosion. Unfortunately, after just 1 year in space, the telescope has astonished experts with its groundbreaking capabilities, providing extraordinary insights into the universe's past. The images from the James Webb Telescope have revealed galaxies so ancient that they could indeed reshape our understanding of the universe's origins. This unexpected discovery has sparked significant interest among scientists and enthusiasts alike. One particularly noteworthy revelation occurred when astronomer Rohan Natu, analyzing early images from the James Webb Telescope, accidentally identified a galaxy that amazed everyone. This galaxy, named Glass Z13, appeared to be remarkably massive and dated back to just a short time after the Big Bang, making it older than any previously observed galaxy. Nata's enthusiasm was palpable as he shared the discovery with colleagues, describing it as beyond anything cosmologists could have ever imagined. The James Webb Telescope, positioned far from typical interference and equipped with state-of-the-art technology, was designed to probe the universe's earliest epoch, known as cosmic dawn. This era, shrouded in mystery, marks the formation of the universe's first stars and galaxies. By examining galaxies from this time, researchers hope to refine their understanding of major cosmic processes, such as the influence of dark matter and dark energy. Initial expectations for the James Webb Telescope's discoveries were modest, anticipating distant galaxies. However, the reality surpassed all predictions. The telescope's images unveiled galaxies of astonishing scale, challenging existing models and sparking a flurry of debate. As scientists continue to analyze the data from the James Webb Telescope, the implications of these findings could be monumental, heralding a new era of cosmological exploration. The remarkable discoveries from this pivotal observatory offer a captivating glimpse into the universe's past, propelling humanity's quest to unravel the profound mysteries of existence. As early galaxies emerged, researchers and onlookers found themselves in a race to understand them. Could this collection of unusually large and brilliant early galaxies be a fluke? Perhaps due to errors in the assessment of the telescope's initial findings, or if true, could they indicate that the universe is stranger and more intricate than our boldest hypotheses had anticipated? The inquiry is nothing less than how we might explain how the precise universe we know emerged from primordial chaos. The early discoveries from the James Webb Space Telescope might potentially alter the fundamental tenets of cosmic history. These elements concern distant ages in far-off galaxies as well as our own existence here in the normal universe. As Mark McCarran, a senior advisor for science and research at the European Space Agency involved with JWST, remarked, "You build these machines not to confirm the viewpoint but to challenge it. You simply don't have the faintest idea how it will be challenged." JWST's observations of early galaxies have been billions of years in the making. However, more subtly, they trace back to the Space Telescope Science Institute in 1985. Around that time, the Hubble Space Telescope was still far from completion. Nevertheless, then-director Ricardo Gen noted that his team began contemplating what could follow Hubble, aiming significantly further afield. Despite initial disagreements over focusing on Hubble, Jan was persistent about the vision for expansive development. Fellow colleague and then deputy director of SD Sky, along with a small team, began drafting ideas that eventually transformed into the next-generation space telescope, later renamed JWST. They noted that while Hubble would be historic, its capabilities would be limited by its observations in visible light. The JWST, in contrast, would operate in the infrared range, allowing it to delve deeper into the universe. The necessity for JWST became significantly clearer in December 1995 when cosmologists conducted the Hubble Deep Field observation. Contrary to expectations of finding a few faint cosmic galaxies, the resulting image revealed an immense number of galaxies stretching back more than 12 billion years into the universe's history. After over 2 decades of development and at a cost of around $1 billion, JWST was finally launched on Christmas Day 2021. The telescope underwent rigorous testing before reaching its crucial orbital destination a month later. By July 2022, it was set to commence its long-anticipated first year of scientific observations, known as Cycle 1. Some aspects of JWST's initial mission were allocated to high-impact programs, including the Cosmic Evolution Early Release Science Survey and the GRIS Focal Point Enhanced Overview from Space, both aimed at unveiling insights into the mysteries of the early universe. As astronomers devoted countless hours to observing independent patches of the sky, searching for early universe's cosmic galaxies, they initially anticipated modest discoveries, akin to a more detailed version of the Hubble Deep Field. However, they were in for a surprise. Stephen Bladden from the University of Texas at Austin, leading the SE project, suggested that extremely distant galaxies should emerge only after multiple data cycles from various projects. Yet, to the astonishment of cosmologists, these galaxies appeared rapidly. The record for the most distant known galaxy belonged to GNZ 11, observed in 2015 with a redshift of 11. Redshift measures the stretching of light due to the universe's expansion, with a higher value indicating greater distance. Yet from the outset of GLASS observations, 2 separate teams, including one led by Rohan Natu, independently identified GLASS Z13 with a redshift of 13, pushing the timeline back significantly further. In their race for quick results, experts relied on work-on methods for redshift evaluation based on brightness estimates rather than more time-consuming direct assessments. Despite their simplicity, these evaluations revealed galaxies surprisingly bright and massive, some previously boasting a glorious mass equivalent to 1 billion suns, similar to our own. The excitement didn't end there. In the following days, several galaxy contenders from Sears and GLASS emerged, some with redshift measurements as high as 20, indicating they existed just a brief period after the Big Bang. These galaxies exhibited disk-like structures not expected in such early cosmic ages. Furthermore, another team found evidence of smooth debris galaxies at a redshift of 10, under 500 million years after the Big Bang. Such a rapid emergence of large galaxies challenges the assumptions of the standard cosmological model, lambda cold dark matter. To grasp this occurrence, a brief revisit to the components of the early universe is necessary. In the moments immediately following the Big Bang, the universe existed as a scorching, dense mixture of subatomic particles. As time passed and the universe expanded and cooled, helium and other light elements formed, resulting in the emergence of primordial particles approximately 400,000 years post-explosion. Around 100 million years later, conditions became suitable for the creation of the first stars, primarily made up of hydrogen and helium. These early stars, larger and more radiant than those we see today, coalesced into protogalaxies, driven by the gravitational influence of dark matter. Nevertheless, findings from the James Webb Space Telescope, JWST, challenged this model, revealing unexpectedly large cosmic structures much earlier than anticipated. Stacy M. from Case Western Reserve University noted the surprising abundance of numerous smaller protogalactic elements, implying that some distant galaxies might be nearer than believed, concealed by dust and appearing dimmer and more remote. The discovery of these early galaxies prompts crucial questions regarding the universe's formative stages, highlighting the necessity for ongoing investigation and updates to our cosmological frameworks. Subsequent observations of GLASS Z13 in August 2022 by the Atacama Large Millimeter Array in Chile cast doubt on the initial findings. Despite using brightness-based methods, ALMA failed to detect significant material linked to GLASS Z13. As P. Tom B. from Goya School, who led the observations, remarked, this implies that low redshift intruders can be ruled out. However, ALMA encountered difficulties in locating the galaxy altogether, underscoring the challenge of verifying discoveries made using JWST's advanced capabilities. Rohan Natu, one of the involved scientists, pointed out the irony, stating, "The good news is there's nothing detected. The bad news is there's nothing detected. Only JWST has the ability to revisit its own observations." The most concerning possibility is that the standard LCDM cosmological model requires revision. Michael Bohan-Cullen, a cosmologist, emphasized the significance of this potential paradigm shift, remarking that these results are quite startling and difficult to reconcile with our conventional cosmological model. Accepting that a questionable hypothesis regarding altered Newtonian components challenges the existence of dark matter would represent a true upheaval. JWST findings might support MZ proposed by Mark McCarran. However, not all cosmologists are convinced of M's legitimacy. Another potential explanation is that galaxies from the early universe might possess minimal material, making them appear brighter and influencing mass calculations. This scenario could also clarify ALMA's difficulties in detecting glass Z13. Charlotte Brickley and her colleagues suggested that JWST could be observing the most luminous energetic galaxies of the early universe, which may indicate intense star formation conditions during that period. David Spergel supports this idea, proposing that the development of high-mass stars may have been more efficient due to increased gas pressures and temperatures, potentially influenced by early gravitational fields. The rapid release of scientific papers stemming from JWST's initial observations signifies a shift towards enhancing peer review through platforms fostering virtual interaction. While this accelerates the dissemination of findings, concerns arise about rushing to conclusions prior to thorough peer review, neglecting calibration issues and potential recalibrations that may affect result accuracy. It seems improbable that the extraordinarily high redshift massive galaxies observed by JWST will be disproven. Ultimately, the sheer number of these galaxies suggests that the early universe may significantly differ from prior assumptions. Bladden expressed confidence in the validity of the discoveries, stating that the likelihood of cosmologists being completely mistaken is slim. Currently, astronomers are racing to align subsequent observations with JWST. Nancy Levinson is reviewing around 12 proposals from various teams, seeking additional viewing time with JWST, primarily to explore high redshift galaxies. Promising new talent is emerging, and given the excitement and importance of these initial findings, validating them is essential. Troy, who submitted one of the proposals, highlighted the necessity of confirming these discoveries. Unique initiatives like Universe Web, led by K2T, aim to expand the known population of early galaxies by scanning broader sky areas for several hours. Overall, they anticipate uncovering many more galaxies beyond previous efforts. They will look for evidence of primordial protogalaxies, potentially using the brief deaths of massive early stars and brilliant cosmic explosions as indicators of their existence. Some estimates propose that JWST could detect galaxies with redshifts as high as 26, just 120 million years after the Big Bang. Confirming even a small fraction of these high redshift candidates would be an impressive achievement, as noted by Natu. This illustrates that cosmologists are undeterred by their findings. JWST has heralded a new era of scientific exploration, and despite the challenges, the swift exchange of new data has invigorated astronomers. Troy expressed enthusiasm for the connected academic community. Now, the question arises, is it the right time to reconsider how we interpret the universe's origins? The significant implications of exploring this overlooked domain conclude the current narrative. Please show your support by considering purchases and engaging with the community for future episodes. Additionally, share your thoughts on the current content. Your involvement encourages us to continue providing quality material and to consistently strive for improvement. Thank you for tuning in, and we'll see you soon. In summary, the James Webb Space Telescope, JWST, has ushered in a new era of exploration and discovery, challenging our interpretations of the universe's origins and evolution. Its remarkable observations of galaxies formed shortly after the Big Bang have sparked excitement and debate among scientists, pushing the boundaries of our cosmological understanding. The telescope's ability to delve deeper into existence than ever before has uncovered cosmic phenomena that defy conventional models, prompting a reassessment of established theories and the development of new ones. From ancient galaxies to the mysteries of dark matter and early star formation, JWST discoveries hold significant implications for our understanding of cosmic history. Looking forward, JWST promises to continue unraveling the complexities of the universe, offering insights into narratives previously beyond our reach. Its revelations not only advance scientific inquiry, but also inspire awe and curiosity about the universe's vastness and our place within it. As JWST embarks on its mission to further investigate the cosmos, researchers eagerly anticipate what new discoveries await. With each observation, we move closer to unraveling the fundamental questions of existence and gaining a deeper appreciation for the tapestry that surrounds us. Ultimately, the James Webb Space Telescope stands as a testament to human curiosity and ingenuity, guiding us toward a richer understanding of our grand origins and our role in the universe's magnificent story.